Alright, you made it. Welcome to the final review lecture. Obviously I can't go over everything, but I'll try to give you the best bang for your buck as usual. So yeah, let's get started. Let's review some stuff. I guess I'd like to start with physical computing, because then we can just go to Tinkercad once and for all and come back to terminal land. So yeah, let's make a circuit that has to do with Arduinos this time, why not? Let's make it so that we've got some LEDs, and they will light up only if we press a button, okay? They're going to light up when we press a button, and here's my button example. So you press the button, the lights light up, and let's say that when you don't press the button, the lights don't light up. I think to keep it easy on ourselves, let's make it so that when you hold the button down, they light up, but they don't stay on. Like, you got to keep pressing it, all right? So that's a simple little example, but a good one for review, because we need quite a few things. All right, so let's drag out an Arduino. Why not? And we're also going to need a breadboard with some LEDs on it, yeah? So the goal is to have these LEDs, 1, 2, 3 of them. Let's put them somewhere nice. 1 LED, 2 LEDs, 3 LEDs, and let's put them right next to each other. They turn on, let's say, when we press this button, all right? And so remember what a push button does. What's going to happen is when you press it down, it's going to connect these two terminals, the ones with the same letter. 1B gets connected to 2B, and then also 1A gets connected to 2A. They're separate places, so you can actually be doing 2 separate things with this button, but we'll just hook into 1B and 2B, all right? And yeah, the goal is we'd like to have the button press be a digital input. We want to feed information into the Arduino to know that we've pressed that button. And then we want to have these LEDs be digital outputs. Okay, so we're going to send information, send power to the LEDs to light them up. All right, so yeah, to give information to an Arduino, we're going to send power back to it. So let's hook into 5 volts and ground here so that we can give power, have this button give power back to the Arduino. All right, so let's see here. Let's do 5 volts. Try to make this pretty. I'm gonna need to zoom out, 5 volts. There we go. Let's have it wrap back around here. And yeah, as pretty as I can make it, there is positive, so red. And then let's have ground as well, negative, coming into the Arduino too. So as pretty as I can make it again. There we go, and then negative as well. Awesome. Okay, so yeah, there's positive and negative coming out, and what we'd like to do is have that power flow from this push button when we press it. Okay, so I guess the best way to do that, right, would be, okay, if we press this button, we better have power coming through, so let's take positive. And the power should be going out to somewhere in the Arduino. So let's zoom out some more. Let's say, I guess in my example, pin 2 is where I want to feed this into. So let's say, all right, when we press this button, we're feeding power all the way to pin number 2. And so that's getting digital input. All right, it'll see a 1 when we press it down. And so I'll make this some different color, so like blue. All right, so that's kind of the goal. It's going to see the power when we press it. It's going to take it from the positive, send it all the way to the Arduino as input, okay? That's what's going to happen there. And when we don't press it, though, it's not actually going to see no power. It's going to get confused for reasons that we've kind of talked about before. So when this button isn't pressed, notice that there's no like negative going to the Arduino yet or anything like that. It's just like the circuit is completely open. There's no power flowing at all. And so along this wire, when the button's not pressed, the Arduino is going to get confused and see a weird like floating value. That's the technical term. And so we would like to make sure that it notices that, oh no, it's just not, there's no power being being sent across. So what we have to do is through a giant resistor, that's usually like, we can make it 10 kilo ohms, it just needs to see negativeness. All right, and that will win out whenever we're not actually sending power. So here, that's how we can do that. We can send negativeness, the black. We can send that over just like that. So when I'm not pressing the button, do you see how there's a way to get a 0? Because like negative is a 0 all the way to the Arduino. But when I press it, positive takes priority. We don't want to like jump over this giant resistor electricity wants to take the path of least resistance all the way to pin 2. So when I'm pressing it, it sees the 1. When I'm not pressing it, it gets the 0 still. All right. So yeah, that's it getting input. And then as for output, we'd like to notice that in a variable. We'll go to code in a second. And we would like to hook in output to these LEDs. All right. So let's say that we're going to use pins 6, 5, and 7. I don't know why I did it in that order. But let's do pin 7, go into this LED, give it some power whenever we want to. And I'll use a different color for this. Let's say green this time. And we'll do the same for pins 6 and 5. These will supply power to the LEDs. All right. Positive, and so they're going into the anode, right, of the LEDs. And we'd also like to make sure, because it's going to be about 5 volts, we'd like to resist a little bit all the way down to negative to complete the circuit, right? Because positive's coming through, we would like to have a way for those electrons to move all the way where they need to go. And so I think I did this ahead of time. It's going to be a 300 ohm resistor. That's a good enough amount here. So resist it all the way to ground. Beautiful. And so we got 3 of those. And so now when there's power flowing, it'll come in through the anode, out through the cathode, down into ground. Perfect. All right. So that's the little pieces. And so the button is input and the LEDs are output. And so let's hook up the code with that in mind. So we've got pin 2 as the input here. So let's just be lazy and use blocks. But you could definitely convert this to normal code, right? So let's get rid of all of these guys. Boop. And what I'd like to do is just have an if else. So I think that's in control. It's like if something's true, if the button is being held down, what I would like to do is light up the LEDs. Yeah. So if reading pin 2 is high, right? Because that means the button's pressed, do something. All right. So where is that going to be? I guess we want to check with math, right? If something's equal to something else. So where's equal checking? It's one of these, right? There it is. This is kind of a pointy comparison. Let's zoom in here. If reading from, let's see, is it input? Yeah. If reading from digital pin number 2, because that's where we hooked in this blue wire, right? If reading from that is a high value, if it's equal to high, where is that said? There it is, high. If it's equal to high, put it right there. Yeah, let's move this out a bit further. So if reading from pin 2 is high, so that means I've pressed the button, it'll see low otherwise, then I would like to light up these LEDs. So I would like to output to pins what? Yeah, output high to pins 7, 6, and 5, all right? So that's what I want there, so output. Set pin 7 to high, and then same with 6 and 5. Duplicate. Duplicate. So yeah, that'll make them turn on because it'll send power. And then otherwise, duplicate. Else, that means if the pin was low, right? That's the other option. We're in the else. Set pins 7, 6, and 5 to low, which is just low voltage, is not going to be enough to actually light up these LEDs. Okay, so that's the goal. And I think that'll do it. Of course, you could do normal code as well. Like you can go to blocks plus text and you can see what's actually going on. You have to set pin 2 as input, the other ones are for output, and then just keep on reading and writing either high or low to the pins that are controlling the LEDs, right? And it looks like it's added a little bit of a delay for us too, to just make sure everything's happy. So yeah, that's that. And let's watch it work. I think I need to go back to just blocks if we want to see all this at once. So yeah, if I turn it on, start the simulation, there's nothing happening because the button is not pressed. The second I press it and I hold it in, see how the LEDs light up? But if I let go of my mouse, unpress it, they go back off again. So it's just noticing it's getting power and it's correctly not getting power otherwise. If I didn't have this resistor right there, it's just going to get very confused. Let me move that away. It's see how they're on right now? If I start the simulation, pressing that, it has no clue what's happening. It does not actually see 0 properly. So that is why we need that. Just in case it's not being pressed, it notices it. All right. So yeah, that is the circuitry. There's the Arduino side. And here is the code and how you would normally write it if you had an actual Arduino. Where is that? I've lost the ability to look at the other kind of code, have I? Really? I legitimately don't see it anymore, the blocks versus blocks plus text. But you remember from before at least, all right? Oh, wait, I have to do that. There we go. So yeah, there's the code. And yeah, I think that's everything that I wanted to show you. A good example of, you know, LEDs, hooking up wires, resistors, all that fun stuff. So yeah, that's a good example to start us off. So that's physical computing. Cannot forget that. You're not allowed. And now let's go to actual assembly. All right, so just let's have just a general review of ARM assembly before we get to fancier things. Let's just make like a main function. And what we'll do is we'll make another function called toUpperAsm. So you know that toUpper function from the C standard library? You give it a character like lowercase a, and it converts it to capital A. So let's make that. Let's make our own version of that in code. All right. And also, if you give it like already a capital letter, it keeps it capital. And if you give it something else, like it's going to return a character back. If you give it like some weird other character that's not even alphabetic, it keeps it the same. So like only if you give it a lowercase character does it actually give you back something different. Otherwise, it gives you back the same thing. All right. And so the secret to making this ourselves is to use the ASCII table. Watch. Do you see how here are the capital characters? 65 is A, 66 is B, 67 is C. And here are the lowercase characters, 97, 98, 99. Do you see how because they're in order, just if you take 97, you subtract 32, that gives you 65. And if you take 98 and you subtract 32, that will give you 66. It's actually a bit. If you just like unset a bit, that would also, I think that's the actual way to do this. But we're just going to subtract, okay? Easier that way. So that should do it. So the lowercase letters are between here and here, 97 through 122. There's A all the way to Z. There it is, 122. So we're just going to have to check, like, is my input between here? If so, I need to actually do something. Subtract 32. Otherwise, do nothing. Keep it the same and return what you were given, all right? So yeah, we're going to make our own toUpper function. We're going to have to call it something other than toUpper because the whole library, the whole C standard library is included by default for us whenever we use assembly programs, whenever we use GCC. So we need a different label name. So let's see, what kind of a name do I want to give this file? I guess I'll call it toUpper example.cpp. All right. So, oops. It's not .cpp, is it? Sorry, I'm in other class mode right now. Excuse me. toUpper. Let's try again. toUpper example.s. There we go. And I would like to steal a main function. Let's take it from some other lecture. Let's try like 17. There's an assembly. Beautiful. So there's a main function. Let's steal it. And let's see here. Let's get rid of all this stuff. Keep the return 0, of course. And yeah, in between, also get rid of this. We would like to make our function first. So let's see. I guess I'll take all this. We'll put it up top here. What do we want to call it other than main? toUpperAsm. Oops. There we go. And so, all right, if this is our function, it's called this. What does it take? It takes toUpperAsm, takes a character, sitting in W0, and it's going to return a character, also in W0, right? So, okay, what are we going to do in toUpperAsm? Well, we just kind of have to check, right? We're not going to call any other functions. We're just going to do stuff, so we don't have to mess with the stack or anything. We just have to check, like, was our input character, was its ASCII value between 97 and 122? All right. So let's check. Let's compare W0 to 97. All right. And if it was greater than or equal to, we have another check to do. But if it was not greater than or equal to, if it was strictly less than, then like we keep the character as it was. So let's call that don't touch this character. Okay. So that's the idea there. And then, okay, if we're still here, let's put don't touch this character down here. I would also like to, if we're still here, we're greater than or equal to 97, we might still be out of the range, so we have to check the other side too. Let's check 122, okay? Let's compare W0 to 122, and we're within the range still if it's less than or equal to, right? So if it's strictly greater than, same game, again, don't touch it, all right? So only if we are still here, if we're still in here, we didn't branch yet, if we are still here, we're within the valid range, all right? So that's the goal. And all right, if we're within that valid range, we're going to subtract 32. Subtract 32 to take it from lowercase a, 97 or whatever, to capital A, which is, I guess, 65, if I'm remembering these right. So subtract from W0, 32. All right? Otherwise, we don't touch it. What does it mean to not touch it? All right, it just means to return, essentially. It's like immediately return, because like if we went straight to there, W0 still has the original character. We just need to return whatever was already there, all right? Otherwise, we messed with it, and we're still going to fall through and return. So that should do it, I think. And now let's, in main, call that function. Let's say, hey, user, give me a character. Let's just be lazy and not give them a prompt. Let's just be like, hey, get char from the library, all right? And then, all right, what's going to happen is this character that we just got from the user is going to be placed in W0. Beautiful. That's where I need it to call this function. So let's immediately, here, I'll split screen it. Immediately, we're going to say, all right, then BL to upper assembly. And again, we're going to get the answer back in W0, which we can then call put char on. Right? It's now the return value becomes the argument to the next function call. And so now I've just printed that character, and we might as well print a new line at the end to like make everything nice. All right, so let's move into W0, the new line character, and print that out. And that looks like a good example to me. All right, so what we're doing is we're getting a character from the user, uppercasing it, printing it, and then also printing a new line so that it's pretty. All right, but this is our function. It's just doing some comparisons and some branches. All right, potentially. So let's compile and run. Boop. And so if it's lowercase a, we get capital A all the way to lowercase z, capital Z, and anything in between. Beautiful. But if it's outside of that range, like a capital A stays a capital A. If it's a question mark, it stays a question mark. So yeah, it seems to be working. And yeah, it's just a general example of assembly just to get us back in the mood to talk about fancier things. Okay? So yeah, let's move right on to fancier things now. Let's talk about SIMD stuff. So what SIMD stands for is single instruction, multiple data. So you're running a single instruction like add on a bunch of chunks of data at once, all right? And so ARM's SIMD processor is called Neon. And so instead of this, right, my favorite picture of SIMD, it's instead of like doing 4 separate add instructions on like A0 register plus B0 register, shove the answer into C0, and the same for the 1s, the 2s, and the 3s, instead of doing all that separately, put them into some very wide registers and have them chunked up, like A0 through A3, put them in one giant V register or something. Put the B's in a different register. And then just say add, right? It's a single instruction. We're adding still, but it's working on multiple data at once. All right, and so that lets us achieve very high throughput, and that makes our programs faster, because this is a common thing to want to do in like a video game or like image processing, or even like you're decoding videos, like you're playing a YouTube video or something. You got to do this kind of thing all at once. So it's important to have this inside of modern day CPUs, and let's remember some of the assembly for it. All right. So yeah, what you get in SIMD assembly is you get 128-bit registers. It's beautiful, right? A lot of room, and you get 32 of those. They're the V registers, V0 through V31. And you first have to get stuff in those registers. You have your loads and your stores for things, all right? And there's a number that goes after those. Load 1 and store 1 are simple, but you can also have different interleavings, right? Different interleavings of data. And so maybe it's like RGB stuff or GBR, because images are sometimes weird and backwards. So that's a thing. So different interleavings. Like I want to get all the reds, all the greens, all the blues in separate registers. And then there's also different sizes of data that you might want to read from memory or store to memory. Okay, so we'll talk about that a little bit more. But for example, for images, each color channel, right, in your RGB format is a byte wide. Okay, so sometimes you want just a byte of stuff. Sometimes you want like 32 bits, like a bunch of ints that you want to work on at once. So yeah, so for example, for RGB data or BGR if it's backwards, we'll use load 3, right? Remember that? You'd say something like this, load 3 into, and then you use curly braces, right? I want all the reds being, because it's interleaved, I want all the reds being loaded into V0, and you say like, how is it chunking up? It's a bunch of byte values, and we can store 16 of them. That's kind of how you read that. 16 red channels of pixels going in V0, and then, assuming it's in order at least, then the greens going in V1, and then in V2 we can put the blues. All right, something like that. And then we say, all right, read that in from some starting location that's in like a normal X register. Okay, something like that. But in general, like once you have it there, you can do some normal operations with similar kinds of formats. All right, so here's like a silly example again. Let's say that we have some information, some 16-bit information, so it takes up 2 addresses per thing, right? And they're interleaved in this way, like it goes, this is thing A, 16 bits of thing A, then thing B, and then it repeats. Here's some more thing A's, here's some more thing B's, just like that, so on and so forth. So it's 16-bit data interleaved every 2. You see that? So if we want to get this out of memory, knowing that we have a starting address in X1, we'll put that there for sure. And it's going to be a load 2, right? Because we have 2 different things. I want to get all the A's, get the A part, all the A's, and shove them into, as many as I can, into one register, and all the B's shoved into some other register, all right? That's how that works. And so if you want 16-bit things, those are half words, so H's, and you can store 8 16-bit things per V register. So like read the A parts into V1 as 16-bit chunked values, and read the B parts into V2 in the same way. All right, so that's the idea there, and that'll take like the red, the yellow, the blue, starting off into V1, also the gray, and then that'll take the B parts, right, the orange, the green, the purple, the darker gray, into V2. All right, and you actually get a few of those. You get 8 of them, 8 half words, 8 16-bit values. All right. So I hope that makes sense and it's coming back to us. But like once you got stuff in your registers, you can do normal operations like add. It just looks like this, right? You say your name of your operation, like add or sub or mul or whatever. You can't divide though. And then you say, like, just as usual, the destination register, but also like how things are being chunked up. Like it needs to know that, okay? Stuff like that. Like V0.16b, stuff like that. So let's say we wanted to add, like, we have all our A stuff, right? A, B, 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 B. It's meant to be a B. Dot, 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 dot. Let's say we want to add all these guys up. Add the A parts and the B parts together into some third register, all right? And so you do that like this. You'd say add, right? Add all these pieces into some destination register that's also a bunch of 16-bit things. So let's put them into V0, and it's also going to be a bunch of 8 half words, right? That's the goal. And add V1.8H. That's how it is set up, V2.8H, all right? That's kind of how that would work. I hope that makes sense, okay? The one thing you don't get is integer division, sadly. Unfortunately. You'll have to find a different way, and I'll show you that actually later, which is exciting. And then the type, of course, can be any of these. You can just use half of your V registers if you're not ready with all the data or you want to do something fancy. I'll show you a good example of that later too. But usually you want to fill it up, like 16 bytes, because we're using images, or 8 half words, or 4 single precision floating point numbers, or integers, normal ints, or 2D, 2 64-bit values, okay? Doubles. So, cool. All right, that's SIMD assembly in a nutshell. I have some examples now. Definitely consult, right, the page, and I think I have a bad link here, so like go back to the actual slides for the good link. But yeah, go back to the image processing code from lecture. I think that's a really good example. I'll give you a few just quick and brief examples today, though. So here's my silly idea. Let's say that we've got an array of what we know to be lowercase characters. Like x0 is pointing to like a C string essentially. It's an array of characters, and it holds exactly 16 of them, or at least 16 of them. So we can process them all at once, right? Because 18 byte values per character. So A, B, C, D, let's say we have 16 characters. So E, F, G, H, that's 8. I, J, K, L, that's 12. M, N, O, P, there we go. That's 16 characters. And let's say we've also got like stuff at the end. We've got, excuse me, OP, and then like a new line and a null terminator, but we're just going to read up to P. Those are 16 characters total. And what we'd like to do is let's capitalize them all at once. Let's get all those characters into a V register, like V0 or something, chunked. We're going to do .16b, right? Chunked up. So like we have a lowercase a there, lowercase b, c, d, and we're going to put them all here, ... And what we'd like to do is convert them to capital. Make them all capital so we can write back to the string and like make it shout out the whatever it's saying. All right. So in order to do that, I need to, well, subtract 32. Remember that example already? It's coming back again. So let's say we got a D there. I want to make it a capital D. Got a lowercase a here. Make it a capital A. So I kind of need, in a different register, right? I need 32 because I need to like line them up, line the A and the 32 up and subtract, do a sub instruction. So I need a 32. I need a bunch of 32s. All right. So there's a couple of different ways to do that, and I'll show you just one very simple way. We'll put a bunch of 32s in the data section too. Why not? All right. And so like once you do that subtraction on each of these pieces, then like this will be capital A, this will be capital B, this will be capital C now, capital D, etc. And then we'll store it right back and have something different to print. Cool. All right. So yeah, let's do that. I guess I just want a main function. Let's steal just that from here. And I'll call it capitalize simd.s. Okay. So that'll work. And what do we want to do now? I guess we need stuff in our data section for sure. So let's get like an actual string. We'll do, no, sorry, not .str, just normal str, please. It is going to be ASCII Z, so C string, and it'll be 16 characters for sure. D, F, G, H, I, J, K, L, M, N, O, P. And then also a new line, and the null terminator is baked in for us because we use the Z. So there's that, and I can read that into a register. I also want to read 32 16 times into a register. There is honestly a simpler, better way to do this, but here's like a simple way to do it. Just like, let's make an array of bytes, each of them holding 32. 32, 32, 32, 32. So that's what? There's 4. Oops. I'm doing my best here. 8, 12, 16. 16 32s to read into some other register. Okay, so yeah, let's get the address of this string first of all. Let's get the address of that string so that I can do some loading, right? It's just going to be a load 1. So load into x0 the address of that string. So now I've got the address in x0, and let's load it now. Let's load 8-bit data, right, in order. So no interleaving or anything like that. In order into V0 is what we said, right? Because V0 can fit, how many? 16, right? 16 8-bit things. That's what we're going to do. So load 1 into just V0, chunked up like this, 16 byte valued things, 16 8-bit things. And the starting address of all that stuff was an x0. So that would take the A through the P. All right, sitting in V0 now. And now we want to do the same thing with the offsets. Boop. So let's load, starting from the offsets into, I mean, we can keep it there. Let's keep it, let's do x1. Keep the old pointer in x0, why not? So we'll use x1 to read the offsets into, let's say, v1. All right, so there they go. So now I have exactly this set up. And now I just want to subtract. Let's subtract back into, well, let's just do the subtraction first. Let's subtract V0, separated, chunked off, 16 byte valued things. V0, V1, and put the result back into v0, let's say, all right? Because then here what I can do is, instead of a load 1, I can do a store 1, right? Back in that same place, because I have not touched x0. I took care to use x1 instead here. So instead of a load 1, I can just store it right back, all right? Store 1. Store back the updated string, and for fun we can print it as well. So I know that x0 already holds the actual string address, but so technically we can just say blprintf, right? So x0 already has the starting address, right? Of the string. That's kind of cool, right? It just all goes together and then it returns 0 as usual. But yeah, here's the code, the relevant parts, right? And we've also got stuff sitting in the data section as well that we're messing with. This should be all caps now. And if we GCC it, in theory, let me check one thing really quick. Oh no, it's making me log in. -o capitalize SIMD. In theory, we should see the alphabet being yelled back to us. Now it's all caps. Isn't that lovely? It's a pretty nice first example, right, of SIMD operations. It's not too horrible, I hope. So yeah, there's that one. I also have a complicated one, just for fun. All right, so here's a complicated SIMD example. Let's do grayscale, just kind of like you did. You did grayscale in your lab for images. But you had to use floating point operations. Like I gave you some weird constants to multiply by, and it wasn't SIMD. So there's another way to do grayscale, because think about it. Like 255 a bunch of times, that's like the max brightness, right? That's white, and then like 000, that's black. And so you can imagine like these RGB values, if they're big, if they're all big, it's like a very close to white value, it's a bright value. And if they're all very small, if they're close to 0, then it's a very dark value. And you can use that to create like that's your range. You can use that to figure out like how light your pixel is. That's another way to do it. So like if we just average together the RGB values, like we were given this pixel, we're looking at this pixel right now, RGB, whatever it is. If we just compute the average, right? Average equals, well, it's R plus G plus B over 3, right? Do you see how if this is a big value, like close to 255, it's very bright. And if it's a small value, close to like 0, it's very dark. So that's kind of the goal. And we can just use that as a grayscale value, right? Because this will be between 0 and 255. And if you remember from when I was first talking about colors, if you have the same value a bunch of times, it's a perfectly neutral shade of gray. So if you just say average, 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 you replace your RGB with average, average, average. That's kind of like averaging together all the lightnesses, and you're duplicating that 3 times, and so it makes a shade of gray that kind of matches the original color. That is one other way to do it. Isn't that cool? So let's do this with SIMD assembly. It's very complicated. I've already written it out. I'll do my best to explain it, but definitely look at the documentation for all this stuff. It's pretty cool. What we have to do, right, is average together stuff. We got to do R plus G plus B over 3. And so we have to divide by 3 with integer division. And I just told you, right, there is no integer division in SIMD assembly land. But there is a way to do it still, all right? And here's like Python program to convince yourself. What we're going to have, first of all, we have to average value. So we have to add up R plus G plus B. They could all be 255. So we cannot use bytes. We have to extend our colors. Does that make sense, first of all? So like these are 8-bit values. We will overflow pretty much always if you're adding 3 8-bit values, right? You need to store the answer for this addition in a 16-bit value. We must elongate things. So what we're going to do is we're not going to use the full V register for once. We're going to read just 8 pixels at a time because like we only need like this many. Is that 1, 2, 3, 4, 5, 6, 7, 8? Because what we need to do is take all these guys, right, and have some extra space, because we want to take these 8 pixels that we just read, like the 8 red values or whatever, and we would like to elongate everything to use up an entire V register with 16-bit, 8 16-bit values, 2, 3, 4, 5, 6, 7, 8, and like take all this, elongate it to a 16-bit thing, because that's going to finally give us room. Does that make sense? Take all these guys and just like elongate each of them. Dot, dot, dot. Because I don't want to overflow. We want to keep the original value. So we can only read 8 pixels at a time, first of all. We want to elongate them. And then to divide by 3, here's the trick. You can do some weird bitwise stuff. All right? Apparently, you can divide by 3. You can take any 16-bit number, and you can divide it by 3 properly if you multiply it by this magic constant in hex, AAAB. That's a 16-bit value, right? Once you multiply, by the way, you're also going to, you need more room, right? Because that's going to make a 32-bit number. Two 16-bit numbers multiplied together make a 32-bit number, don't they? Right? Just like if you multiply two 3-digit numbers, you're going to get like max 6-digit as an answer, right? So same thing's going on. So like if we're multiplying two 16-bit values, we need 32 bits of space. And then we take the answer and we shift it right by 17. Magically, that will do the same effect as dividing by 3. And here's a Python program to test every possible 16-bit value to prove that that's true. It's very wild and very cool. I'm not going to teach you how or why this works. It's just a magic thing that we can use. Okay, so that's the goal. And here's the code. I've spoken enough. So I've made it's just a grayscale folder. I've already programmed it all. I'm going to try to walk you through it. Ask me if you have any questions. Look everything up in the documentation page, but here's kind of the goal, right? You're just like everything else. Where am I? Like the filter.cpp. This all exists. We're going to do it as we did before. We're going to call, it's going to call this grayscale SIMD function on a bunch of pixels. It's going to tell us how many, all right? Guaranteed to be a multiple of 16, so we can do our cool SIMD stuff. But here is how you process them and compute their average and replace that, okay? Watch. So, all right, first we have to loop as usual. So W1 is the number of pixels. We're just going to keep subtracting from that and checking if we're done, right? So there's that part, and then down here is the part where like, yeah, we just processed 24 things, right? We're doing 8 pixels at a time, not 16. All right, we're looping some more, all right? We're doing 8 pixels at a time, not 16, because to compute an average, you have to add up a bunch of 8-bit values and they might overflow. So we have to elongate first. That's the first step, all right? So step 1 is, all right, we're going to read in our first chunk of pixels. So x0, we're just going to keep advancing x0. So read in just 8 at a time, all right? Only into 64-bit, half of the V registers, all right? And I know that the diagrams and everything else have taught you that if you do just half of the registers, it's loading into the right half of the registers. I am here to tell you that that's kind of a lie, all right? And so we're going to imagine that reading into just half of the registers is really reading into the left halves only, all right? That'll make more sense later with some other instructions, all right? So what I've got now is I've got 8 pixels sitting in, this is what? This is V0, V1, and V2 are holding a bunch of pixels, all right? So just the reds, the greens, and the blues, but not in that order technically. So I've got these values, right? Red, or green, sorry, blue, green, red, right? Backwards. V0, V1, and V2. So like we're just using the right halves, or think of it as the left half this time though. 1, 2, 3, 4, 5, 6, 7, 8. This is what's going on. That's V0, V1, V2. What I need to do next is elongate those guys, all right? Because I want to be able to add things together. So I'm going to use V3, V4, and V5 and elongate these things, all right? Does that make sense? So just take the original, take the left halves of V0, V1, and V2, elongate them into the full width of a register, but as half words instead of byte values. So we're extending unsigned values. That's kind of how you read that. So that's that. That's what we're doing next. I know it's a lot to think about, but we're doing that next. And so now in V3, we're taking that and we're doing, we still have 8 things, but now they're longer, 16-bit values, right? We're doing the same for V4 and V5, right? Same idea. Because now we have big pieces, right? We have big pieces that will not overflow, all right? So that's very nice, and now we can add them all up together. if I can draw 8 halves properly. There, so now we've elongated everything, okay? That's what we've done. And then we can add them up all into just V3, all right? So we're adding up all these pieces. We're about to compute the average, right? So in V3, we still have a bunch of 16-bit values that represent the sums of the R, G, and B values, okay? So there's that. And then we need to divide those values in V3 by 3, and so to do that, we have to do our weird magical constant multiplication. So I get my magic constant in a bunch of things, right? I'm going to take my magic number, here it is, in the data section. I'm taking it, I'm shoving it into, I'm duplicating it into every part of V0, apparently, as a half word, right? So it's dupe for duplicate, which is another way that we could have done our previous example. So now V0 holds my magic number as a bunch of half words. Again, you don't have to fully understand this example. It's just a good one that shows you like the power of everything. So here's AAAB, AAAB 8 times, and this is like the sum for the first pixel. This is the sum for the second pixel, blah, 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 all right? And so now we're going to do a multiplication instruction. We're going to multiply these guys, these guys, these guys, and these guys. And we need extra room, right? These might overflow 16-bit values, and so what we're going to do is we're going to do a special kind of multiplication. We're going to multiply and elongate at the same time, because two 16-bit numbers multiplied together create potentially a 32-bit number, all right? So we need extra room. So we're going to multiply elongated, so it's multiply with an extra L, okay? Multiply V3 and V0, just the left half, all right? So think of it as just the left half when I say 4H, 4 half words, right? Just take this chunk, these two chunks, multiply them together, and shove their answers, we multiply just these, into a bunch of 32-bit values in V1. So into V1 goes a bunch of 32-bit values, and we can only fit 4 of them, right? We're making them bigger. So this is like the multiplication result 1, multiplication result 2. For the first 4 pixels only. We need extra room in a different register. We're going to use like, what did I say? V2 for the other ones. So this is the right halves being multiplied into V2. Do you see like the problem now? There's a lot of elongation going on now. So like we've got some like these, this is pixel 5, right? Pixel 5, pixel 6. And so we got to keep them in order. And so that's what's going on. V1 is the left half, V2 is the right half of our pixels. For just the 8 that we originally read, right? There's a lot of work going on. And then I've got the multiplication result. I have to shift right now. All right, shift right by 17 for each of these bad boys. Shift right by 17 for each of these things, and this is V2. And so here I am shifting them right, shifting them right, shifting them right. And so now eventually in V1 and V2, I have my answers, and I just need to shove them back where they belong. All right, so if you shift right by 17, you finally have a normal 8-bit answer again. And so I can take them back, I can shrink them down, take this 4S thing, take all of it and put it all the way back to where it belongs. All right, so like, let's see. What's the best way to think of this? So like V1, shrink it down into the left half of V0. So like we're putting all their answers back in V0 right now as 16-bit values, first of all. So this is being shrunken down into just the left half, right? The left half of V0, and this is going into the right half of V0, being shrunken down into 16-bit values, and then we're going to shrink them right back down once more. Take the 16-bit values, shrink them back into 8 bytes. Just take that and finally turn it into V0 again, but not to scale. This is getting ugly, I know, but the left half as just byte-valued things. So that's why, that's the long-winded example of why we could only use 8 things at a time, okay? So I don't expect you to fully understand this example, but like there we go. I have my average value that I can then store back as the red channel, the green channel, and the blue channel. Those are my averages. Yay, all right. So cool, they're all back. Like place them into V1 and V2 for fun so I can do the exact same opposite idea of this. Like I had a bunch of load 3s, I can do just one store 3 now because I'm shoving the answers right back. So yeah, take your time to read this yourself. Eventually, I promise it will make sense, and I can help it make sense in your mind. But like, I've finally got average values. Just put them back as the red, green, and blue channels, or I guess blue, RGB backwards is BGR. Put them back to where they belong. And then I just processed 8 pixels, and each pixel is three colors, right? 3 8-bit things, so 24, so 8 times 3 is 24 bytes total that I just messed with. Advance, all right? And keep looping, and that'll do it. Like, that's the trick, and that's one way to grayscale things. So like here, if I compile this, filter, how do I have to use this? Filter grayscale on campus1.bmp, and I'll call it campus1.gray.bmp. And so it did it in the blink of an eye, and let's see, I guess the best way for me to show this to you is to like commit this to Git real quick. And of course I'll give you the changes that I do right after this too. But yeah, it's up there now, in theory. Let's take a look and see if it grayscaled it properly. So this is, boop, that one. 45, final review folder, grayscale. So there's the original, there's the new one. Moment of truth. So there's the original picture. There's the grayscale picture. Lovely. Awesome. So that's another way to grayscale things, if you just average together all the values. It's going to give you a slightly different look, ever so different than what you did in your lab. But it is an equally valid way to do things, and it's a great example of all the weird stuff that you might have to do in SIMD sometimes, just to get division happening. All right? So yeah, that is enough of that. You can look at that example if you'd like. But let's keep on trucking. Let's talk about the rest of the things I want to talk about. All right, let's talk about virtual memory. So remember, secretly now, like, we're not actually touching physical memory. That's the operating system's problem. Every time we run a program, it's getting its own virtual memory space that the operating system manages, that like makes it so that we have our own bytes of memory that nobody else could ever possibly touch unless they like hooked some electronic things into the RAM chips themselves. All right, so yeah, we get our own virtual memory space per program, and the operating system is going to map that to physical memory. We're still going to like some pieces, some chunks of our program are going to be mapping into physical memory still, but they could just as easily be mapping to places on the disk because we don't have enough room for everything. Okay, so yeah, for example, like if you go to like if you run two programs, they're both gonna think that they own all of memory. Like they're gonna see this, they can write to the smallest addresses, they can write to the largest addresses. Pretend we only have 32 bits of space for now, but we get 64 bits. P1 has its own like view of the world, and P2 has its own virtual view of the world. All right, 3, 4, 5, 6, 7, 8, all the way to FFFF. Pretend we're on a 32-bit machine to save my wrist. Is that 8? One more F there. The idea is like you're going to use chunks of memory, and like it's always a different chunk. Like P1 talking about this chunk of memory, it's going to be mapped in a different place actually than P2 at that same set of addresses. It might go to a different place in RAM. Like that one might go there, that one might go there, or something. That's kind of the goal. All right. So that's the secret. That's how you think of it. All right. But they also could be mapping to the disk or something. That's something we've had to offload for some reason. Okay. And so every time you read something, every time you read an address in your program, it's a virtual address, and like we need to figure out where it really is. Like am I going to physical memory right now? Do I have to go read something off the disk? That's the operating system's problem. And we use the memory management unit to do that mapping. Right. So the operating system sets it up. Every page, right? Every virtual address goes to the MMU, and it's like, okay, CPU wants to load this address. The MMU is like, okay, this is a virtual address. We're talking about process 1's memory right now, and so this is going to map to a physical address right now, and it's just 104. All right, so it really wasn't that original one. Okay, And so that's where the RAM goes, and it's like, okay, yeah, CPU, you wanted that value of this virtual address. I just figured it out for you. That's where it really was, sitting there, right? So yeah, every time we read something, it has to go through the MMU to figure out, like, where is this thing really? Is it actually in physical memory right now? All right, and so the granularity at which we do a mapping from virtual memory to physical memory is called pages. We break things up into chunks. We break memory up into chunks called pages, and that's what we store. Like we map pages in virtual memory to frames in physical memory. All right. So yeah, we break the virtual address space into pages, and 4 kilobytes is the usual size that people have agreed upon these days. But it doesn't have to be that size. Like Mac OS likes to be different and use 16 kilobytes, I just learned, instead of 4. But like Linux still likes 4. Doesn't matter though. All right, and so yeah, that's the idea. And so there's going to be a correspondence between 4 kilobyte chunks of virtual memory to physical memory. And so it's pages are the virtual things, and they're mapped to physical frames. All right. And that mapping is stored in a page table, we say. So here's kind of the setup. Like this is like, and the page table knows about where every page is. It stores that mapping. So kind of here's the full picture of what goes on when your program tries to read memory. It's like you're reading a virtual address. Your CPU is like, all right, go to this address. It's really a virtual address because it's a user space program. And so the very first step is to figure out, all right, this virtual address lives in some page somewhere. Like, all right, so let's figure out which page is this bad boy living in. That'll give me a page number. All right, I'll give me a page number, and then that page number is mapping to some physical frame somewhere. And I need to go and look up, if this is process 1, I need to go look up in its page table, like which page does this address correspond to. So look up in page table happens next. And that'll give me a frame number, most likely. It'll be in physical memory somewhere. Here's the frame of physical memory where that thing lives. All right, and so now I know, like, okay, I'm gonna go look. This is the actual place. This is the actual page that is in physical memory somewhere. There's the frame where it lives, and now I'm going to go to whatever offset. The virtual address had a page number and an offset into that page. So you're gonna go into that same offset. Like, which offset do I need to go to? Same offset. Go there. Right. Take that offset, that same offset from the virtual address. Look it up at that same offset in the frame you were given back, and that's finally the memory that you wanted. That's the actual place in physical memory that you need to go to actually get your value. So that's the MMU's job. So that's the memory you wanted. All right? And so yeah, that's your end goal. Like, figure out where the page table is, go look there, like that's where that page was being mapped to in physical memory. That's really the frame, okay? And so here's just an example of that again to remind us of everything. So here is a page table for 2 separate processes, because they're each going to map to different physical spaces, right? And let's pretend to be an MMU and translate virtual addresses to physical addresses, all right? So let's assume the following. We've got 8-byte pages, all right, 8-byte pages, 7-bit virtual addresses, okay, and 6-bit physical addresses. So here are my 7-bit virtual addresses. We're going to map those to physical addresses, and it's got to be 1, 2, 3, 4, 5, 6 bits long, right? 6-bit physical addresses back. And because our pages are 8 bytes, you have 8 bytes per page, and each address, it's a byte address, right? So how many bits do we need to store offsets in that case now? So that's the new question. All right, if I have 8-byte pages, what can I store? Like, how do I move around, right? If every page is 8 bytes, I need to be able to offset into that page, right? If there's, I need to be able to go to like offset 0, right, all the way to 0, 1, all the way to offset 7, right? That's 8 bytes total that I can access. So how many bits do I need to store that offset? It's going to be, well, 0, 0, 0. Well, I guess look at the biggest value. 7 is 1, 1, 1. So we automatically are going to need 3 bits for our offsets for our pages. And so even if we have lower values, you have to pad them with zeros. All right. So that means our page offsets are 3 bits, and that means our page number is a 4-bit value, okay? And so that's the goal. And so that means when we're translating from virtual to physical address, like the rightmost 3 bits, that's your offset. That's stayed the same. And so it's really like, this is our page number right there. We need to figure out its frame number, all right? So it's, if it's 6 bits total, like this is going to be, this 4-bit value becomes a 3-bit thing for physical addresses, all right? Because automatically, these are offsets. They're being taken along for the ride. Like this offset, all of these are offsets. We're going to take that same offset from the page into the frame, okay? So now we know. So like whatever this physical address is, it's going to end in 100, right? That's the first thing. It's just like, what are the other 3 bits now? What does this page map to? Which frame does it map to? So, all right, it depends on the process. Each process has a different page table. So P1 is trying to read page number 0. It's trying to read from page number 0 now, all right? So, all right, we're going to go to entry 0 in the page table, and it is a valid, this page, it's a valid page right now. It's going to map to an actual frame, and it looks like it's frame number 3. So in 3 bits, right, because that's where we need to store this, our frame number for page 0 is frame 3. That's what we're mapping to, okay? And so take these guys, map them to 3 bits. The number 3 in 3 bits is 11, padded with the 0 at the start. 11. So the final physical address is this one, right? 0111100. Isn't that cool? That's the idea. That's the trick. And so we're going to do the same thing a bunch of times. So like whatever frame this ends up going to, it's the 000 offset. And it's process 1 is going and looking at page 1 again, or sorry, page 0 again. Still valid. Let's map into frame 3. So it's still going to be 011. All right, so that's the physical address. It's part of the same frame, actually, just a different offset. That's pretty cool. And so let's do the rest. I encourage you to try the rest. Pause the video if you can. But like, all right, I'll do this quickly now. So process 1, whatever frame we're ending up at, whatever address we get, finally, it's going to end in 000 again. But now we're going to page number 2. See that? 10 is 2. Look up at page 2. It's valid, so we can read from it right now. It's in physical memory. It looks like it maps to frame 6. So 6 is 110, and so that becomes your physical address. See that? And now I'll try to do the rest faster. So all right, now this process 2 is going to also go to the same address. You see this? It's the same address. Same address, but it's going to be a different physical place because you can't have them clashing like that. That's the beauty of virtual addresses. It's a different address space. So all right, we got process 2 is going to page 2, which is valid. It maps to frame 5. All right, so that's going to be 101, so that's 5, and then offset 0. So they're both going to the same address, but they're really stored in different physical places in RAM. That's pretty nice, right? Process 2 also trying to read this page number 1 now. So page 1 is valid, and it's mapping to frame 4. So 4 is just 100, and the offset is the 010. All right, so we took that and we translated it. All right, and then process 2 is going to read this. Again, it's going to read page, what is that? Actually, what is that? 1, 2, 4, 8. 8, 9, 10, so 11? Yeah, so page 11, which is invalid right now. Oh no. Oh no, whatever shall we do? All right, so let's say, all right, this is what happens. Now, it would be at frame 3, but actually somebody else is using frame 3 right now. So what we got to do is evict somebody. So to make this valid, we have to make this one invalid. You see that? They can't just both be using the same place. Like, we'll write this to the disk or something, and we'll read this off of the disk. It was cached, all right? It was swapped out is the way to say. So we have to go to the disk, make it valid eventually. Now it's in RAM, and it's going to be at frame 3, so 011, and the offset is 001, all right? So that's what happens when you have finite memory space. You got to kick some people out sometimes, right? And now process 1 also wants to go to page number 11, which is valid, and it's going to map to frame 7. So 111, offset 001. See that? So yeah, that's how that works. That's how that game works. And virtual memory is just a really nice abstraction for us, right? It makes the world go round. It's very wonderful. So yeah, I think that's all that I wanted to say about that, the last thing I want to talk about, I guess, is interrupts and signals. All right. So yeah, you have a mouse. Here I am clicking my mouse. I'm typing my keyboard buttons, whatever. Every time you do that, you have a device doing something, like it needs to tell the CPU that something happened, and that's called an interrupt, all right? Also, when you make a system call, it's you, the programmer, making a special software kind of interrupt, all right? And that forces the operating system to notice that something's happening and like take over and do something that needs to be done, like read, figure out which mouse button I pressed. Was it left mouse or right mouse? And like what were the coordinates? Which key did I just press? Stuff like that, all right? So yeah, software interrupts triggered by the two things, triggered by syscalls, like your SVC, whatever, as well as signals, like your Control-C and stuff. So Control-C, remember, that's called your interrupt signal. SIGINT is its fancy 6-letter name for some reason. And I'll show you an example of catching that, all right? So let's be silly. Let's catch a bunch of SIGINTs and like not let it end the program, all right? So like maybe we'll let it end the program only if the user gets lucky and like we pick a random number between 0 and 9, like we flip a 10-sided die and it comes out 0, all right? So with a 1/10 chance, maybe it actually ends the program. Otherwise it mocks the user or something. So that would be a fun example. All right, so yeah, that's, oops. I did not want to do that. I probably just messed something up, but whatever, I need to get back out anyway. So new file, call it catch sigint.cpp. Finally, we're writing C++. And yeah, if I'm gonna do randomness, I need a bunch of things. I need cstdlib for randomness, and to see the random number generator, I need ctime. And then to do signal catching stuff, it's a couple extra headers from just like the Linux library. So it's signal.h, and then it's gonna be unistd.h. which I don't really remember. Unix something, Unix standard probably. I don't fully remember what that means. But we don't have to remember. It's just, all right, let's do initialize the random number generator if I'm going to be obnoxious like this. And all right, what we're going to do is let's handle sigint, which is Control-C. And we're just going to have that as a constant because I included the library. So here's what we're going to do. To set up a signal handler, you say signal, and then you say which one you want to catch, sigint, and then you want to say what you want to have happen, like which function should be called, which signal handler function gets called when this happens, and I'll make a function called sigint handler, right? And it's got to be a special kind of function too. It's got to be a void function with that name, sigint handler, and it's got to take an int. And that int is actually a signal ID. So really, you could have set up the same handler for multiple signals. You'd be past the ID of that signal. So we're only just going to catch sigint. We don't have to worry about this parameter, but it needs to be there. All right. So yeah, what do we want to do? Usually we'll just like mock the user. Haha, I'm not going to let you end me, new line. But sometimes we'll be like, okay, if flipping a coin, flipping a 10-sided die with a 1/10 chance, we'll actually end the program. See how? Okay, fine. We'll be silly, and it'll be exit 0 to end the program from there. And then yeah, just like keep the program running with an infinite loop essentially now. Because like if it stopped, if it returned 0, the program would stop. So like, well, true, there's a pause function that just like waits for the next signal, which is kind of what we need here. So it doesn't like make the CPU too hot. It's like it's waiting in a nice way. Waits for the next signal to occur. All right. So yeah, that's kind of the process. Can I show you everything relevant at once? Pretty much. Nice. So yeah, there's catch sigint .cpp. And yeah, if I press Control-C, most of the time it's not going to let it end the program, but with a 1/10 chance, it actually will. Depends on how lucky you are. Looks like it only took 2 that time. But yeah, that's a fun example, and that is technically an interrupt. You pressing Control-C, it's telling the keyboard that something's happening, and that eventually alerts C++ / the operating system, right? But like hardware signals are another way of giving information to the CPU. Like when the network card, for example, when you like ask to go to some website or you refresh a page, like you have no clue how long that server is going to take to respond to you. So that's a hardware interrupt. Like the CPU is just waiting, and the hardware is going to be like, it's going to alert the CPU with an interrupt whenever it's ready. Okay, whenever your internet data is ready. So yeah, I think that's all that I want to say about the review. That's plenty of topics to go over, but hopefully that was somewhat helpful to you. Do come to office hours, ask me plenty of questions if you want to know more. But I think that's a good start for you. So yeah, good luck, and I will see you later.